In this video, we're going to be deriving all of the AP Physics 1 formulas for Unit 2 Forces and Dynamics. So whenever you approach a problem, you want to start off with drawing the free body diagram, then choosing axes that align. Then you want to write Newton's second law separately in each direction, where you sum the vertical forces and the horizontal forces. Then you want to substitute in your force formulas. And then fifth, you're going to solve algebraically. So summation of your forces is equal to mass times acceleration. You can solve for acceleration of the system by taking the summation of the forces, dividing it by the mass of the system. And that's the same thing as the net forces, because that will be equal to the net result. So let's start off with our first scenario in forces and dynamics. You're going to have a single block on a horizontal surface with no friction. You're going to have an upward normal force, and you're going to have a downward force of gravity that's equal to the weight. So here, your normal force is equal to your weight. In the horizontal direction, you're going to have the summation of your forces. X is equal to ma times x. F is equal to ma. So A is equal to F over m. So the only horizontal force is the applied force, so it alone is going to be causing the acceleration. Now, what if you have a single block on a horizontal surface that has kinetic friction? So in this case, you have this block and kinetic friction, which is going to be Fk. So if you have this block that is pulled horizontally by the force F, and it's sliding across this rough surface, we still have our normal force acting upward, and we still have the weight force acting downward. We are also going to have the summation of our forces in the y direction equal to ma times y, which is the normal force minus mg, which is equal to 0, and normal force is equal to mg. You're going to have your kinetic friction formula, which is mu k times the normal force, and your normal force was just mg, so that is your mu k, your force of friction. So now in the horizontal direction, we have max. So you have the force that you applied in a direction. This is going to be your positive direction. And you have a force of friction acting in the opposite direction equal to ma. So you substitute in mu k, mg is equal to ma. So A is equal to your force minus mu k times mg divided by m. So you could also rewrite this as A is equal to F over m minus mu k times g, because you can cancel out that m from that second term. Now, what if you have a situation where you're pulling on a block at an upward angle with friction? So instead of pushing it down, we're going to be pulling it this way. We're going to be pulling it with the force that we apply, and we have friction. So at this point, we have Fk. We still have mg. We have upward normal force still. So we have in the vertical direction equal to may, you have Fn acting upward. But since this force is not directly on our axes, you're going to have to decompose this into Fx and Fy. So this is your angle theta. You can see that this is your adjacent side. Your adjacent side is going to be related with cosine theta times the force. And then your vertical direction is going to be F sine of theta, because you have this as the opposite side and this as your adjacent side, and that is your hypotenuse. So you have Fn plus F sine of theta minus mg is equal to 0. So solving for Fn, you get mg minus F sine of theta. Force of friction is still going to be equal to mu k times normal force. So then this is going to be equal to mu k times mg minus F sine of theta, because we just found that normal force is equal to this expression here. Now for our next step, we are going to take this summation of the forces in the horizontal direction. So you have ma times x, and you have F cosine of theta acting in the rightward direction, and then in the left direction you have the force of friction, Fk, is equal to ma. So you have F cosine of theta minus mu k times mg minus F sine of theta is equal to the mass times acceleration. So if you solve for acceleration, you're dividing everything here by m. Acceleration is equal to F cosine of theta all of that divided by m. So that's your acceleration, because if you pull upward, that's going to decrease your normal force. So your Fa is going to decrease your normal force. and decreasing your normal force is going to decrease your force of friction. Now, what if you are pushing on a block at an upward angle with friction? So it's going to be this scenario, except instead of having your force acting in this upward direction, your force is going to be acting in this downward direction instead. So you're going to have the summation of your forces in the y direction equal to mass acceleration y. In the upward direction, you still have Fn, downward you still have mg, and you have F sine of theta acting downward this time because this is going to be a downward angle, and then this is going to be to the left instead for your Fx. That's all going to equal to 0, so Fn is equal to mg plus F sine of theta, and you have your force of friction is mu k times the normal force, so that's going to be mu k times mg plus F sine of theta. So if you look at your horizontal direction, you have the summation of your forces in the x is equal to ma times x. So you have F cosine of theta acting in the direction. You have Fk, and then you have ma. So you have F cosine of theta minus mu k times mg plus F sine of theta. And then that's equal to ma. So after this, a is equal to F cosine theta minus mu k mg plus F sine of theta, all divided by your mass. Now, if you are having your force applied increase, you're pushing downward. So if you push downward, that is going to increase the normal force since you have to have more force to support your object above the surface, and that is going to increase the force of friction that you experience as well. You're still going to have normal force upward, you're still going to have Fg downward, you're going to have your force applied to the right, and then you're going to have a force of static friction that's opposing it to the left. So you're going to have a rough surface, so your coefficient is not equal to 0. Fs max can be represented as mu s times your normal force. Here your normal force is equal to mg because you only have two forces acting in the vertical direction, and also you have no acceleration in the vertical direction as well. So you get that your force minimum required is going to be equal to mu s times mg. So the applied force must beat the maximum possible static friction in order to start moving the block. So this has to be overcome. Now, what about if you have two blocks pushed together on a frictionless table? Well, you are going to have acceleration of both blocks and also the contact force between the two blocks. What you're going to do is you're going to treat the two blocks as a system. So everything in the system is m1 plus m2. So you're also going to have a net external force, and this is going to be in the horizontal direction, and we're going to call this F. So we're going to use Newton's second law. F is equal to m1 plus m2 all times a. So acceleration is equal to the force divided by m1 plus m2. So how can we get the contact force? So your force contact is equal to m2 times a. So if we're looking at just m2, we can see that the only force on m2 is going to be the contact force between m1. So if you substitute in your acceleration, you still have m2 times F divided by m1 plus m2. So that is going to be your contact force. So this is going to be the force that you have to contact in order to accelerate your block m2. Now, what if you have two blocks moved together with friction? If this is our surface table, again, we have a block 1 here, another block here too. This is m1, this is m2. You are going to have the same kinetic friction, mu k, and we're going to treat this as a system again. So for our system, we're going to find the F net equal to ma. So our external forces, we're going to have a F that is going to be pulling it forward, and then you're also going to have a separate mu k, or you're going to have Fk1, and you're also going to have Fk2 pulling it backwards. Now we have to find the total friction, so you have to find Fk total. That's going to equal to mu k m1g, that's normal force, plus mu k m2g. And you can just factor out your mu k times g, giving you m1 plus m2. Now, if you do Newton's second law, you have F minus mu k times g, m1 plus m2. That is all going to equal to m1 minus, or m1 plus m2, all times acceleration. So acceleration is equal to F minus mu k times g, m1 plus m2, all divided by m1 plus m2. So that's your final formula for acceleration. You could also just write this as F m1 plus m2 minus mu k over g, because you can write that as just 1. Now, our applied force is going to move both of the blocks, while the friction from both of the blocks are going to resist the motion. Now, we have two blocks that are connected by a string on a frictionless table. So these are our blocks. We have a M1 and we have another M2. We have a string that's connecting them. So if they're connected by the string, and then a force is going to pull on M1, so this force is going to pull. We are going to find acceleration first. So F is equal to m1 plus m2, because we're considering this as a system together, because the string has to be moving with the other string, times A. So A is F m1 plus m2. Now, how can we find our tension force? So if we look at m2, we can see that the only force on m2 is going to be this tension force this way. So that tension is going to be equal to m2. So this is for m2, by the way, m2 times F, m1 plus m2. So that's going to be equal to m2 times F divided by m1 plus m2. Now, what about when we have two masses that are connected by a string on a friction table? Well, it's going to be basically the same setup, except we have friction this time. So M1 and M2 are going to be connected by a string and pulls across a table with a rough surface, F. So they both are going to have this coefficient mu k. We have to find the total friction. That's going to be equal to mu k M1 times G plus mu k M2 times G. So that is mu k G M1 plus M2. And you have F minus mu k times G M1 plus M2 is equal to M1 plus M2, all times acceleration. So A is going to be your force minus mu k times G M1 plus M2, all divided by M1 plus M2. So if we look at M2 specifically, we can see that we have a tension that is going to be forward, and on the point of contact on the floor, you're going to have a force of kinetic friction, just like we had one over here. It's FK2, and then this is going to be FK1. So FK2 is backwards. Now, if we do Newton's second law for this object, we have T minus mu k M2G is equal to M2A. Tension is equal to M2A plus mu k M2G. So we can actually substitute in our acceleration, which we have over here. T is equal to M2 times F minus mu k times G M1 plus M2, all divided by M1 plus M2, all plus mu k times M2 times G. So this can simplify down to just tension is equal to M2F, M1 plus M2. So if they both have the same mu k, since they have the same mu k because they're on the same surface, therefore our force of friction is going to cancel out in our equation for our tension. Now, our friction is going to slow down the whole entire system, but it's also resisting our trailing block. So the only tension, so the tension only needs to provide the block share of the applied force that is pulling forward. Now, what if you have an Atwood machine with two hanging masses? So an Atwood machine means we have like a pulley like this, and we have two hanging masses. So let's say we have M1 and M2. So if we have M1 over here and M2 here, let's make M2 bigger. M2 is greater than M1. So then on M1, we're going to have a tension, and then we're going to have an M1G downward. You're also going to have a tension here, and you're going to have an M2G downward. So for M1, let's make our upward direction be positive, and for M2, let's make our downward direction to be positive. So let's write the respective equations. We have T minus M1G is equal to m1a, and then here we have m2g minus t is equal to m2a. So now let's just add the two equations. We are going to have this is equation 1, and then this is equation 2. So 1 plus 2. This is going to be t minus m1g plus plus m2g minus t. That's going to give us and this is equal to m1a plus m2a. So you're going to have m2g minus m1a is equal to m1 plus m2 times acceleration. You can factor out a g, or you can factor out a g here. This is a g, by the way. And you have m2 minus m1 is equal to m1 plus m2 times acceleration. So acceleration is equal to g m2 minus m1, all divided by m1 plus m2. Now, we found acceleration, but we also want to find tension. Let's actually move this over here. Make some room for tension. Well, we have t minus m1g is equal to m1a. So we can rearrange for just tension as m1g plus m1a. So let's substitute in our a. m1g plus m1. This is our expression for acceleration. So basically we just took this. Now this is going to become m1g so we get and you have 2m1 m2g all over m1 plus m2. So that is your force of tension. So both masses, they share one acceleration because they have to be moving together. Your heavier side, it creates that unbalanced net force, which is what causes our acceleration in the first place because of the unbalanced forces. Now for our next question, we are going to have a hanging mass that pulls on a frictionless table. Well, we have a block M1, we'll call this M1, that sits on this frictionless table and it's connected over a pulley to a block M2. So for M1, you have that tension is equal to M1A. Now for M2, you have that M2G minus T is equal to M2A, because we're going to make this our positive acceleration direction, and then we're going to make this our positive acceleration direction. So after this, we're going to substitute into our hanging mass equation. We have m2g minus m1a is equal to m2a. So we're solving for acceleration. So now we can find tension as well. So you're taking this, so your hanging mass weight is going to be the thing that is driving our entire system. Now, what if you have a hanging mass pulls on a friction rough table? So similar setup. This is our M1, this is our M2. So for M1, we're actually now going to have a friction force. m2. So Fk's friction is mu k m1g. Now for finishing m1 off. So we're just adding them. So that's your full acceleration. You can factor out g if you want to. You have mu k, m1, all over m1 plus m2. Now we can also find our tension. So rearranging for just tension. So this is our tension. And we see our hanging weight again is driving the system, but the friction on the block is resisting the motion, which is why it's going to degrade a little bit of M1. What about a block sliding down a frictionless incline? Okay, so for incline problems, you have a block without friction. You have normal force here at the center of mass. You also have a mg cosine theta. Theta, that's your mg sine of theta. So what about our perpendicular direction? You're gonna have your perpendicular forces. So normal minus mg cosine theta is equal to 0, because we're not going to be lifting off of the table. Now, what about our forces parallel to the incline? We only have mg sine of theta, which is gravity pushing this block down. So acceleration is just equal to g sine of theta. Now, that's the only that component of gravity is going to be causing our acceleration. So what about a block sliding down a rough incline? So in this case, if we had friction, mu k, so this is actually a case without friction. So let's put this over here, but let's make another case that has friction. It's going to be just like this. The only difference is you're going to have a force of friction. So your normal force is still equal to mg cosine theta. That's the only force you have in the vertical direction. And your friction is equal to mu k times normal force. We just found normal force, so mu k mg cosine theta. Now take the forces in the parallel direction. This is going to be equal to sine of theta minus friction, because we're going in this direction for acceleration. Let's divide by a. I mean m. So we have that cancels out, and this cancels out. You can also factor out one of these g's, So gravity is pulling down the incline while friction points up the incline. What about a block that's sliding up a rough incline? So it's going to be similar to this, except you're going up now. So we can change our coordinate system. We're going to make up the incline as our positive direction. So now we have the friction pointing in the opposite direction because it's still opposing. This is going to be mu k mg cosine theta. So let's take our normal force, that's g cosine theta. You have summation in parallel direction, ma. You have negative mg sine of theta now because it's the other direction. Acceleration is equal to negative g sine of theta minus mu k times g times cosine of theta. So then you have acceleration again. You can factor out that negative g from each of the terms. And it's a negative g actually. So then you're just going to switch that sign there. You have mu k times cosine of theta. And what if we just want the magnitude of this? So this is going to be g sine theta plus mu k cosine theta. So the block is moving up, but we have gravity and friction that are opposing our motion here. Now, what if we are trying to find the minimum angle for the block to start sliding down a rough incline? Well, let's take our setup again. So that means that you have a threshold. So we have this angle here, that's going to be angle, and the angle is going to be slowly increasing. So that means that it's going to go from this to this. We want to find the minimum angle that it will start sliding down. So we are going to have our parallel direction at rest. And also normal is mg cosine theta. So we're going to say we have then we can just divide both by cosine theta. That's going to be tangent theta. So that is going to be mu s. And if you want to just get theta by itself, you can take inverse tan. That's going to be your answer as well. So you're going to start sliding when your downhill gravity component equals your max static friction. That's when you have to overcome that force of static friction, because like this is Fs and we want to go down, right? Block at rest on an incline with static friction. So if it's just at rest, we actually have this is what static friction is, but that is not always the case. Because static friction is only going to be maximum. Fs equals max only when object about to slip. Okay, parallel direction. vertically, we just have these two, so they're equal. Now the Fs condition is going to be this. If we have Fs less than mu s times normal, so plugging in, we have mg sine of theta less than or equal to mu s mg cosine theta. What we can cancel out is that mg. So our condition is going to be when we have our sine theta is greater than or equal to mu s cosine theta. That's going to be when tan theta is less than or equal to mu s. So Fs is equal to mg sine of theta. This is going to be our actual, but our condition for rest is this. Now, what if we are pulling on a block up an incline with no friction? If we're pulling up an incline at an angle theta, we have along the incline or you could write this, canceling out that other m. So your applied force that pulls up the ramp is going to be up, and then you're going to have your gravity's parallel component that's pulling down. So this is pulling up the incline without friction. What about if you were pulling a block up with friction? If you had friction, that means that your block is moving up, so friction is going to be pointing down. So let's take this. Let's also draw out the situation for our previous question. So in our previous situation, we had no friction, so you were pulling up on the block. You basically had this force going up, and what that looked like was just the force. So this is how we just got our situation. Now if we're pulling up with friction, now you're going to have your force up and you're going to have a frictional force. But this is actually going to be kinetic because we're having movement. So Fk is going to be mu s times mg cosine theta, because it's mu s, or actually mu k, because this is kinetic. That's the normal force. So along the incline, we have F minus Fk is equal to ma. All divided by m. So our gravity and friction, they're both going to be opposing our motion. That Fk downwards is opposing motion, and gravity is also opposing motion downward, because your force is acting upward. So now what about a block that's pulling down an incline? Or you're pulling on the block downwards on the incline. So you have your force that you're applying is going to be down this way, and you're going to have a frictional force opposing Fk. So along the incline, after we know that in the vertical direction, we just have mg cosine theta is equal to normal. These two are equal. You can just take along the incline. Force is going to be this direction of acceleration, so if mg sine of theta and minus friction is ma, so F plus mg sine of theta minus mu k mg cosine theta is equal to ma. So A is just F plus mg sine theta minus mu k mg cosine theta, all divided by m. So that's your formula. Your applied force and your gravity, they both point down the ramp, while friction points up the ramp. Now let's continue to our next question. What if we have a hanging mass that pulls up a frictionless incline? So let's just draw this out. If we have this hanging mass, we have M1 on the incline. Okay. And you're going to have this pulley, and on the other side, you're going to have an M2. So our M2 is going to move in the downward direction, and you're going to pull up here. So for M1, we're going to make upward positive. This is all for M1, by the way. And for M2, we're making downward positive. Now let's add 1 and 2. So we get this. You could also just factor out G. And you get this. Now our hanging weight is going to compete with M1's weight. So that's why we go downward for M2, and then that pulls M1 down too. So they move together. That's something you have to remember, that you're moving together. So what if you have a hanging mass that pulls the block up the rough friction incline? So M1 is on this rough incline, and you actually have friction this time. So for M1, M1g sine theta minus Fk, because you have Fk acting in this direction, it's going to point the opposite way, is equal to M1a. And then for M2, you have M2g minus tension is M2a. So let's add 1 and 2. M2g minus M1g sine theta minus mu k M1g cosine theta. And then this is important. It's going to be M1 plus M2 times A. This is our system mass, and this is going to be our system acceleration. So this is M2g, M1g sine theta minus mu k, M1g cosine theta, all divided by M1 plus M2 for acceleration. And here you can also factor out your g. So you have your g, M2 minus M1, so you remove this M2 minus M1 sine theta mu k. You remove that g as well, so you have cosine theta. So your hanging mass pulls, and gravity and friction on the incline block are going to resist. So what if you have an incline that's pulling your mass upward? So if we're going up and we have our mass, say we don't have friction. So if M1 slides down, and it's pulling M2 up this time. We're reversing the direction, which means that M1 is greater than M2. For M1, we have M1G. Sine theta minus T is M1 times A. For M2, we have tension minus M2G is equal to M2A. Let's add 1 and 2. Factor out G from numerator, you have M1 sine theta minus M2, M1 plus M2. So the incline component of M1's weight, which was, so you had no friction here. You had mg here, right? And then you had your mg sine of theta, and you had your mg cosine theta. That was your angle. This was your angle. So this incline component of m1 g sine of theta is going to be greater than the hanging mass weight m2 g. Is going to be greater than just m2g. So now let's talk about if we had an incline block that is sliding down and we had a pulling mass up. So this is going to be in the case where we actually have friction. So this is going to be friction does not equal to 0. In this case, we're still going to have m1 greater than m2 because m2 is going to be going upward. For m1, we have now for m2, upwards positive. So now we just add 1 and 2 again like we've been doing. We have m1g sine theta minus mu k, m1 cosine theta minus mu m2 g is equal to m1 plus m2, all times an acceleration. So acceleration is m1g sine theta minus mu k, m1 cosine theta minus m2g, all divided by m1 plus m2. And again, you could factor out g. Minus m2, all divided by m1 plus m2. So your gravity is going to drive that ramp down, your entire system down, and your friction and your hanging mass, they're going to resist. So here we had your Fk, and this hanging mass is going to try to be pulling it the opposite direction. Those are resisting. Now let's talk